Again, welcome everybody. Just a short introduction first to ISES, for those of you who don't know us. The International Solar Energy Society is a nonprofit UN-accredited membership NGO. Our vision is 100% renewable energy for all, used efficiently and wisely. ISES represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. We work together with like-minded organizations from countries all around the world to advance the renewable energy transformation. We are a membership society, and there are many benefits to joining ISES. You can find out more about our work on our homepage. Some of the benefits include exclusive access to presentations and webinar recordings, such as today's in the webinar archive. ISES members also get discounts and even free registrations to ISES events and our partner events. Every month, ISES also publishes a newsletter for our members where you can follow our progress and share your news as well. Members can also subscribe to our academic journal, Solar Energy, which is our flagship publication. So we welcome those who are not yet members to join today and to support our work. For those who are already an ISES member, we thank you for your support. Now, some brief information about the webinar today, and especially the Q&A section before we start. We have 3 presentations for you this evening, or this afternoon, this morning, depending on where you are in the world. Our expert speakers will give their presentation, and this will be followed by a question and answer part of the webinar for you, the audience. We invite you to send in your questions, and we're looking forward to your participation. When sending in your question, you can do so directly on your panel on the go-to screen. Please write who the question is for and keep your questions short and precise. Our moderator, Bärbel Epp, will be moderating the question and answer part of the webinar. So please feel free to start sending in your questions anytime throughout the webinar. Now I'm happy to introduce you to our moderator for today, Bärbel Epp. Bärbel will introduce you to our speakers and guide us through the question and answer, as I said, session. Bärbel is the founding and managing director of the German consultancy Solrico for solar market research and international communications. She is responsible for the international newsletter on the web portal www.solarthermalworld.org, which reports exclusively about market and technology trends in the solar heating and cooling sector. Now I'm very happy to hand over to Bärbel. Bärbel, thank you again for joining us today. The floor is yours.
Thank you, Jenny. Good afternoon to everybody. I'm happy to welcome you to this webinar on thermal energy. As you know, this is a very dedicated topic for the energy transition, storage materials, and thermal storage in general. And we have 3 very dedicated speakers today with us who will present us their know-how and their work. Now, I think I want to show you some slides on the IEA Solar Heating and Cooling Program. If I get the, oh yes, that's it. I hope it's all visible. Well, the IEA Solar Heating and Cooling Program, which is co-organizer of this webinar, is one of the very established and first IEA technology collaboration programs. We have about 20 country members, the European Commission, and 4 international organizers. That means that more than 400 experts from all 5 continents group, and they work in particular solar research-oriented projects. And I name some of these topics. This is a wide range. We work on PV thermal, district heating, historic buildings, industrial solar heat, industrial water management, facade integration, and neighborhood planning. And as we will hear today, about thermal storage material development. You can have different channels to join and to get to know our work. There are these webinars which are also recorded, and you can find the recordings and the presentations afterwards on our website under this link. We actually regularly interview experts on their topics and on our conferences, and we have added some new interviews now on this playlist, which you find on the IEA SHC YouTube channel. Also, on request of partner countries, we organize online trainings. The last ones have been in China, South Africa, and UK. You can visit our website. Feel free to answer questions to our secretariat and follow us on social media, which is the hashtag IEA SHC or a LinkedIn group, which is also under our name, as well as YouTube. We have a webinar today, as I already said, and Jenny said as well, material and components for thermal energy storage. Actually, Task is the word for an international research project within the IEA Solar Heating and Cooling Program. So we give them numbers to be easier to communicate about them internally. Our first speaker is Dr. Wim van Helden. He heads the Thermal Energy Storage Group of the Austrian Research Institute IETEC since 2014. He is originally from the Netherlands, where he studied physics and did his PhD at the Eindhoven University of Technology. He was 11 years responsible for the group, which was called Thermal Systems in the Built Environment on the Research Center in the Netherlands. Together, Wim is co-chairing this Task 58, which is a 3-year project and ends at the beginning of 2020. Wim will give us an introduction into the general work of this international research platform, which is covering all sorts of storage tanks. Hope, Wim, you have your screen ready and you can give us your presentation. Thank you very much.
Thank you, Bärbel, for this kind introduction. My presentation will come now on screen. F5, yes. This first part, as said, is a general introduction on the work on materials and component development for thermal energy storage, or Task 58 Annex 33. What you will hear and see in this part is, say, the motivation for doing thermal energy storage, how the annex is and task is working, which some examples of work that we do, and then also some future steps that are needed to make sure that the technologies of compact thermal energy storage are being brought into practice. To start with, the purpose of energy storage is that the technology is a sort of enabling technology for a lot of fields, for instance, for solar thermal or for district heating or for biomass, solar thermal power. Thermal energy storage is a key enabling technology. This is the left-hand side of the picture. Another reasoning for having thermal energy storage is in the so-called flexible sector coupling. More and more renewable energy is being generated in the form of electricity, and to be able to benefit from this electricity in several sectors, so for instance the heating and cooling sector, but also mobility, energy storage is needed, and especially thermal energy storage is needed to provide heating and also cooling to the heating and cooling sector. There are 3 main principles for heat storage. Most known is the sensible heat storage, and to the right you see a picture of the amount of stored heat as a function of the temperature of the storage medium. And for sensible heat, this is a linear relationship, meaning that with increasing temperature, the amount of heat that is stored is also increasing. This is the most practical form of heat storage, and mostly it's done in water, sometimes in other liquids or in solids. Other forms of thermal energy storage are the compact thermal energy storage forms. One is the latent heat, and the other one is the sorption heat and chemical heat, or thermochemical heat. Latent heat will also be treated by the second speaker, Christoph Rathgeber, in a few minutes. It discusses the work on phase change materials, and these phase change materials have the property that in a certain temperature range, the melting temperature or evaporation temperature, a lot of heat is taken up by the storage material. And this is depicted here to the right in this figure, where you see that at a certain temperature there is a jump in the heat that has been taken up by the material. Typical examples of phase change materials are ice, having the phase change at 0 degrees centigrade, and then organic materials like paraffins, or inorganic phase change materials like salt hydrates. The third class is Thermo Chemical, subdivided into sorption storage and chemical reaction storage. Here the principles of thermal storage are either physical or chemical, and in general there's no uniform picture of how the enthalpy increases with increasing heat, increasing temperature. This is very dependent on the type of reaction or the type of material. In general, these two last classes are being treated and also studied in the Task 58 Annex 33. We call them the compact thermal energy storage. What is the purpose of having compact thermal energy storage? The first is that it has a higher storage capacity, meaning that you need less volume to store the same amount of heat. And this is very important in those areas where the volume is very costly. Another quality, especially for thermochemical materials, is that the losses are minimal. So this means that heat can be stored for long periods without virtual losses. And this makes them especially attractive for long-term storage. Another reason for using compact thermal energy storage is that the materials could have an added functionality. For instance, for phase change material, the added functionality is that most of the heat is being stored at a certain fixed temperature, meaning that those materials also can be used for instance for comfort heating or comfort cooling. For sorption material, there is the property that moisture is being taken up by the material, leading to the added functionality of drying functionality of this material. The challenges in general for thermal energy storage is that that it is dependent on the application, meaning that the temperatures at charging and discharging determine which material can be used in which application, next to the charging and discharging powers, for instance. And the challenge, therefore, is that there is no direct relation between the material properties, the material data, and how this material will perform in a given application. Knowing these challenges, we followed a certain approach in the task, which one of the approaches is the 4-temperature approach for thermochemical materials, and this is depicted in this figure. To the left-hand side of the yellow dotted line, there is the charging cycle. There is a source giving heat through a heat exchanger to your thermochemical storage vessel or storage device. But you also need the ambient to get rid of this heat. So therefore, 2 temperatures are important at the charging phase, the charging temperature for the material and the ambient temperature at charging. And then 2 other temperatures at discharging are important. The temperature at which the consumer needs the heat, and the temperature at that time of the ambient. So there's a cycle for charging at the left-hand side, and there's a cycle for discharging at the right-hand side. And these 4 temperatures determine what the quality of or the performance of the material will be in a certain application for thermochemical materials. Another typical example of how we work is that when designing an application for thermal energy storage, we first start with the material. For instance, these zeolite beads here in the top figure. These materials have certain properties, and these the material properties will determine how a reactor will look like. In this example, it's a reactor for another material. It's a solid sorbent reactor, absorption reactor. And the qualities and the performance of this reactor will determine how the system will look like. So we have a design approach that from material going to components and then to the system. But we need another cycle that goes in the other direction, first calculating what the system performance is for this component and that material, then going back to the component and see what we can improve of the component. Then we have a component performance, and from this component performance, going back to the material, see if we can change the material in order to have a better performing component. And this cycle needs to be gone through several times in order to have an optimized system for a given material and a given component. And that is what we do in this task. The task is an international collaboration within the International Energy Agency. It's task 58 because this task is coming from the program Solar Heating and Cooling, and it's Annex 33 because it's coming from the program of energy conservation through energy storage. We have a 3-year working time, started in 2017 and ending this year. And the typical working is that there's a gathering of experts every half year, and these experts are both from the material side and from the application side. So we have a good collaboration between the materials experts and the people knowing how to integrate a storage in a certain application. Next to working on the own projects, the experts also work on common goals within the collaboration. This is the task structure. We have 2 lines. One line working on phase change materials, the vertical line here along the subtasks, and then another vertical line on thermochemical materials. Then we start with the first subtask on determining the boundary condition for relevant applications in order to be able to develop components and materials for these applications. This is a common task for phase change material and for thermochemical materials, and the other tasks are divided into 2 parts, one TCM and one PCM part. Subtask 2 is about the development and calculations of improved or new materials. Subtask 3 is on measuring procedures, but using measuring procedures that look into the application conditions. And subtask 4 is on the development, so the design and development of components for these innovative thermal energy storage materials. As an example for the materials development, you now see here in this graph, as a function of temperature here on the x-axis, the energy storage capacity for a given application, and this time the application is for room heating. And on the x-axis, the temperature is given at which the material is being charged, the so-called desorption temperature, because at the moment we are looking into sorption materials. The black triangles show the performance of these sorption materials in this application for the pure sorption materials. And the new development now is that to this sorption materials, other materials are being added, salt hydrates, and this leads to a composite material that has better performance. You see this in the performance of the materials with the blue squares, and especially this lithium chloride and impregnated in vermiculite material. It has a double performance of the average of the sorption materials. So this is an important development within the subtask on materials. Another example is for the chemical reactions. Note that here the temperatures are much higher, starting with 300 degrees centigrade up to 800 degrees centigrade. And here is the reaction enthalpy depicted. So typical reaction enthalpies are very distributed for the different materials. Here to champion here is the magnesium hydroxide oxide reaction with expanded graphite, which shows that it's between 350 and 400 watt-hours per kilogram of enthalpy change at the temperatures of about 370 degrees centigrade. This example shows that there's a lot of work going on for finding new material pairs and new material reactions for typical applications. And here the applications are for storing industrial heat. How this material then is used to charge and discharge is an example here from the Technical University of Munich as an example of component development within the task. This device is constructed as a cyclone reactor in which calcium oxide is being mixed with water vapor and then forms calcium hydroxide plus heat in the form of 104 kilojoules per mole. And the challenge with this reaction is to get the heat out at the proper temperatures and get the heat out in an effective way, in such a way that all the particles containing this heat are being brought into good contact with the walls of the reactor. And then this reactor is being used to have cycling, and up until now the technical feasibility was showed or demonstrated up to 20 cycles. Another example of component design is for the phase change materials. Here at the Dalhousie University in Canada, work is being done to design rules for optimizing PCM heat exchangers. And in order to find these rules, different configurations in form of different sizes, different geometry, different PCM material and operating conditions have to be first defined and then experimentally characterized in order to find out what the design rules are. Here's some examples of different geometries. On the top figure, it's a plate heat exchanger, tube heat exchanger, and the lower figure gives an example of finned tube and coil heat exchanger. An example of an application research that is being performed at my own laboratory, my own institute, AE Intec in Austria. We work on compact thermal energy storage for the seasonal storage of solar heat. And to the right here you see the reactor which has a square shape. This contains salt hydrate, and the salt hydrate is being charged and discharged, and when it's being charged then water vapor goes through the condenser, which is on top of the middle vessel, and then the condensed water is being stored in the bottom of this middle vessel. And the right vessel is the vessel that is the interface between the heating and cooling of the house and the hot tap water of a house and the compact thermal energy storage system. We developed this storage module for 200 kilograms of salt hydrate, and now a system of 3 vessels is being demonstrated in a house in Poland. These were some examples of work that we do. It's impossible to give all examples because it's more than 40 projects from different groups all over the world working on the different aspects of compact thermal energy storage. What is the further development need for compact thermal energy storage? So what are the things that we should work on also in future? We also saw that there is a need for thermal energy storage to replace fossil fuel supply of heat demand and to reduce the necessity for large electricity transport capacity in future, because not all energy can be provided by electricity. And therefore, we need thermal energy storage, but thermal energy storage can only be applied if we have a cost reduction. And this can be achieved by having better materials, having better design components, and integrate these components and materials in the best way into a system. These are the working fields for the compact thermal energy storage. And we see that first cost-effective applications will be in the sectors power to heat, industrial heat, and in those sectors that have added functionality for compact thermal energy storage. So what are the next steps in future to make sure that compact thermal energy storage find its place in the energy world? We will continue with the design approach, working on materials, components, and the systems. We couple compact thermal energy storage research and development to the high potential application areas. We find novel ways for the development processes. We have to formulate new challenges for continued IEA collaboration, not only in our fields, but also perhaps in other fields for system integration and digitalization. And we will address some challenges through mission innovation activities. And one of them is already starting. It's working on a roadmap for thermal energy storage materials acceleration platforms. And last but not least, what we also need to do is provide the decision makers with good information on the potential and the necessary research and development steps for compact thermal energy storage. This is what I would like to show about this part, this introduction, and I'm happy to answer your questions.
Yeah, thank you, Wim. I think this was a very good interview, overview of a complex research field, really impressive with 30 projects you are managing. And I think this shows already the value sort of this international research platform, that you exchange and that you learn from each other and profit from each other experiences to speed up this important field. So Wim, thank you very much. And we go over to the second speaker. We have today 3 speakers, and we will go through their presentations first, and then we have a Q&A session. So you're very welcome to type in your questions in the meanwhile. Our next speaker is Christoph Rathgeber. He's working as a research assistant in the Thermal Energy Storage Group at ZAI Bayern, which is a Bavarian research institute in Germany, and he is there since 2012. He is, as Wim already said, a dedicated expert on latent heat storages with phase change materials. And he has been participating in IEA Solar Heating and Cooling programs since 2013. His topic today is material development for low temperature latent heat storage. Christoph, I'm looking forward to your presentation.
Thanks for your introduction, Bärbel. Good afternoon from my side. My presentation today is about the development of materials for low temperature latent heat storage. For this purpose, we are using salt hydrates and mixtures of salt hydrates. And here is the outline of my today's presentation. First, I'd like to give you the motivation for using salt hydrates as phase change materials and latent heat storage systems. And then I will show you how these mixtures are being developed and characterized. And at the end, I'd like to give you an application examples where these kinds of phase change materials are applied. So first, let's start with the basic principle. As Wim already showed, the first technology to store thermal energy is called sensible heat storage. there is a almost linear relationship between the amount of stored heat and the temperature. That means rising the temperature rises the amount of stored or released heat. Now looking at phase change materials, the situation is as follows. If we look at a certain temperature range between two temperatures, and if a material undergoes a transition from solid to liquid state in this temperature range, then the amount of stored heat is comparably higher using phase change materials than sensible heat storage medium. So in most technical applications, the interesting phase change is from solid to liquid and the other way around. Examples of this technology, as Wim already introduced, is ice, the transition from ice to water at 0 degrees C, or what is also very well known are these heat packs. They are using a salt hydrate with a melting temperature around 58 degrees C. So as you see on the figure, PCM phase change materials provide a high amount of stored heat in a narrow temperature range around their phase change. And that means that each application requires a material with a suitable transition temperature, let's say suitable melting temperature. For the low temperature range, salt hydrates are most interesting. On the left, you see a figure with the different material classes that are being discussed or applied as PCM, several organic and inorganic materials, and in the range from 0 to 100 degrees, salt hydrates offer higher melting entropies in terms of energy density per volume at comparably low costs. An example of a salt hydrate would be calcium chloride hexahydrate. So the salt is calcium chloride, and 6 moles of water are coordinated around the salt. However, there are today several temperature ranges without cost-effective PCM, and as pure substances are mostly known, we are developing salt hydrate mixtures to create new PCM. So how does it look like to develop salt hydrate mixtures as latent heat storage materials? In our case, we were following this line of development. In the first step, we calculate mixtures, and therefore, we do this to identify eutectic mixtures. I will show you later on why we are doing this. After the calculation, the predicted eutectic composition needs to be experimentally verified. If this verification is successful, we are performing thermal cycling tests to test the material under application conditions. And if also these tests are successful, then we have developed successfully a new PCM. So for the first step, the calculation of eutectic mixtures. Why are we doing this? Here, a simple phase diagram is shown in the figure. So to keep it simple, the line illustrates the solubility threshold, or illustrates the transition in temperature between the liquid and the solid. So above the line, everything is a liquid solution, and below, several or different solid phases precipitate. And as it is marked here in this system, lithium nitrate and water, there's a binary eutectic, and this is interesting as to be used as PCM. If we would, for example, cycle it or use it in the temperature range that is shown here, then we can expect a reproducible transition from solid to liquid and vice versa, and this in a short temperature range. So eutectics, in theory, they have a reproducible phase transition, and as binary eutectics, as the example shows one, are mostly known, our approach is to calculate ternary systems containing 2 salts and water. And in this case, in the case of ternary systems, the example given here is lithium nitrate and magnesium nitrate in water. Now we have different liquidous surfaces in this diagram. So you see the base of the diagram, that's the composition triangle, and in the vertical direction, the temperature is plotted. And here are the different solid phases that occur in the system, the 2 anhydrates and then several salt hydrates. What is interesting in terms of PCM development is now the location of the ternary eutectics. In this system, there are several 2 types of eutectics occur, ternary eutectics and so-called pseudo-binary eutectics. And so for the calculation, the result is the composition and the temperature of these eutectics as given, as indicated in the table at the bottom. So for the pseudo-binary eutectics, we have 2 solid phases in equilibrium with solution, and in the ternary eutectic, there are 3 solid phases in equilibrium with salt solution. So having calculated, having predicted these eutectic compositions, it's important to experimentally verify the calculations. So at first, it's important to determine the concentration of the salt solutions we are measuring. Therefore, we determine the water content using either a moisture analyzer or titration. A different type of titration is also used to measure the concentration of different salt ions. Then having, let's say, verified that we are measuring what we want to measure, so having verified the concentration of the salt solution, we are performing calorimetry. So now the presentation stopped. I don't know why. Let me check this. Okay, I think I started again from this slide. Okay, so now we can go on. The second step is to perform calorimetric measurements. Therefore, we're using a DSC, differential scanning calorimetry. To explain it a bit more in detail, I'll give you a brief and easy, rather simple example. So here it's the ternary system containing ammonium nitrate, lithium nitrate, and water. Shown on the left is the phase diagram, the 3 solid phases that occur here, and indicated as a black ball is the location of the ternary eutectic. So in the calculation step, the information that we get is the 3 phases that are in equilibrium with the salt solution, their composition, the eutectic composition, and the eutectic temperature as indicated here. And now we are performing calorimetric measurements, DSC measurements, with the sample of that composition. And in this case, it's an example of a successful verification. And there's a successful verification because what we observe is a single and quite narrow melting transition. So this is shown by the red curve. Blue one is upon cooling, the red one is upon heating. So this eutectic is experimentally verified. The next step is to perform thermal cycling tests. The idea of thermal cycling tests is to validate that the PCM can be used over many heating, cooling, melting, crystallization cycles, and thereby taking into account the requirements or the conditions of the applications. So what we are doing in thermal cycling is shown on the right. Is shown the temperature program. So that means we have the PCM, and this is subjected to repeated heating and cooling. And what we found out, what is very important and also very useful, is to have a visual investigation of phase separation, and therefore we measuring the eutectics in such transparent bottles, put them in a thermostatic bath, and then we're taking pictures during the thermal cycles. And this is shown on this slide. At the top, you see the situation after the first cycle. So both samples shown here are completely in the liquid state as they should be. So this is the situation after cycle 1 at the high temperature. However, after cycle 15, you can see for sample number 60, there's some kind of solid material at the bottom, which indicates phase separation. And then continuing the cycling after cycle 135, there's still some solid material on the right sample at the bottom, but what is also visible is that the amount has slightly decreased. So there seems to be a kind of stabilization process. Now I'd like to show you a possible application of salt hydrates in the context of low temperature latent heat storage. The application is a system providing solar heating and cooling with the combination of an absorption chiller and the latent heat storage. So how does it work? At day, the system is driven by a solar thermal collector, providing heat at 90 degrees C to a thermally driven absorption chiller, which in turn provides cold at 15 degrees C to a cooling system. And to keep this process running, heat needs to be rejected. So this is now the green circle. Heat needs to be rejected at 40 degrees C. And in this case, this is done partly by a dry recooler and partly by storing the heat in the latent heat storage. Storing here means melting the PCM. Of course, to regenerate the storage at night, the system is operated in that way that the latent heat storage is unloaded using colder air of the night. For this system, we were using calcium chloride hexahydrate with a melting temperature of 29 degrees C, which suits well to the application temperatures. On this slide, you see a picture of the storage that has been used in the installation. As I said, the PCM is calcium chloride hexahydrate with a melting temperature of 29 degrees C. There are two types of storages, one with 1 and one with 1.5 cubic meter storage volume. And as you can read, the capacity is either 80 or 120 kilowatt hours in the temperature range between 22 to 36 degrees C. So what is the special feature of this type of storage is we're using a so-called capillary heat and tube exchanger, which is immersed in the liquid PCM. So the blue capillary tubes are made from plastic to account for the corrosive properties of the salt hydrate. And the picture in the middle shows the PCM crystallizing on the surface of these capillary tubes. With this system, it has been in operation for several years, and here you see the results of the thermal cycling at storage level, and again applying charging temperature of 36 and a discharging temperature of 22 degrees C, and thereby we could validate the thermal cycling stability for this material in this storage configuration. So now I'd like to come to the summary of this presentation. Material development of low temperature latent heat storage has been carried out in several steps. The first point is to develop PCM based on salt hydrate mixtures. This is done by calculating solid liquid phase diagrams to identify eutectic mixtures, and then by experimentally verifying the predicted compositions using calorimetry. The second step would be to perform thermal cycling tests in order to check the long-term performance of these materials. And as you have seen, it is very useful to visually investigate the phase separation, or to visually investigate the phase transition, and thereby being able to investigate possible phase separation processes. And in the end, this material development can be transferred to the concept of low temperature latent heat storage using an immersed capillary tube heat exchanger. And also at this storage level, it's important to perform testing under application conditions to ensure the long-term performance of these materials. That's it from my side. Thanks for listening, and I'm looking forward to the Q&A session.
Thank you, Christoph. To let us look a bit into the really laboratory work, this provoked a lot of very dedicated questions that we will raise at the end. And we will give the floor first to Benjamin Fumey. He is a research engineer and a PhD candidate at the Swiss Federal Institute for Material Science and Technology. He is electrical engineer and has more than 12 years of R&D experience in thermal storage. One of his current focus research areas is components and systems for sorption-based seasonal thermal storage for buildings. Today he will speak about component development for liquid sorption thermal energy storage systems. So Benjamin, I'm looking forward to your presentation.
Okay, thank you very much for the introduction. Yeah, we're gonna go right into looking at some of the activities that we did in subtask 4, components and system development, and I'll use the work that we're doing on liquid sorption heat storage as an example. Now, exactly, as Wim had already mentioned, we've got a whole lot of different demonstrator lab scale systems being reported, and all sorts of different processes, and of course power and capacity and applications found. And we see that one of the main focuses, or the challenges, is really the heat and mass exchangers for these sorption heat storage systems. Now, exactly, and what we've understood is that we need a common basis really to make a comparison of these systems and to understand progress in the field. So in our subtask, we've found these two basic evaluation levels, which we see here, the 4 performance criteria. One which we call gross temperature lift, then of course volumetric energy density, power density, and finally round trip efficiency. And we see that we've got this, we can do this evaluation on 4 basic different levels: material, bulk, component, and on a system level. And what we also see is we've got all sorts of varying process types and many different temperature profiles being used. So in other words, to be able to get a common basis for comparison, we need to first define some realistic temperatures, and we've gone into looking at what are realistic temperatures. And what I'll show here now is the temperatures, a part of a temperature definition that we have made for a building application. Because as we know, sorption heat storage works as a chemical heat pump, and temperatures very strongly affect the performance of the material component and of course finally of the system. Without going much further into these temperatures, here you see Wim had pointed out we need charging temperatures, we need ambient temperatures for a heat sink, we need source temperatures in discharging, and we in this case here need a certain space heating temperature. With defining these temperatures, it is possible to actually evaluate right from the materials, from the milligram level materials to the system, performance of material in component and in system. So this is one of the very important initial common grounds that we have defined now for building applications. We see we've got all sorts of varying systems, and looking into this, the question is it possible to sort of define basic processes of these different systems, to be able to look into the basic processes, and even there already find some of the possible performance reductions coming from material to the system level. We've defined systems as follows, comparing open to closed here on the x-axis, referring to exposure to air, and transported and fixed, referring to the sorption material being stationary, meaning fixed, or being transported, as would usually be done in a liquid sorption heat storage. In the transported. So we have four basic storage processes that we've defined, and further details would be found in the publication mentioned below. Just a brief point to set here is that we do find that the closed transported system has some benefits to the others in respect to closed having a higher vapor pressure, and thus in discharging a better discharging performance, and also transported being able to absorb, to cool down the absorbent further, especially if there's a counterflow process between the heat transport fluid and the sorbent, and thus being able to discharge better. So we already see that the choice of system process does have an effect on the performance of the material. Going on now with the temperature profiles that we have defined, we can on a material level evaluate the maximum the performance of such a material, and it's very important. I show this here now for sodium hydroxide. We have the water vapor pressure on the y-axis, temperature of the aqueous sodium hydroxide on the x-axis, and of course depending on what sort of temperatures I work with, I get a different performance here in respect to the temperature lift, the gross temperature lift that I require for the charging, which is the upper line, and the gross temperature lift that I'm able to reach in the discharging, and of course, very important in the discharging also, the minimum concentration that that I will get, which then defines my or leads to my maximum energy density that I can reach. Here, just to point out, you see in the red dashed line is the fact that in our case with sodium hydroxide, we do not want to go beyond 58% because we have a liquid sorption system, and sodium hydroxide tends to crystallize above 58% in room temperature. So we already see here now with these defined temperatures, we see we have a slight limitation in our case with sodium hydroxide in the application. Another method to present this, which is a sort of a mapping, which is nice to start with a theoretical performance, and then also place into this diagram the performance of components and systems is what we see here. We have on the x-axis the gross temperature lift, which means the temperature difference between the desorber and the condenser in the charging process, and the evaporator and the absorber in the discharging process. On the x-axis, on the y-axis, we have the mass fraction or concentration of, in our case, of the sodium hydroxide. And the blue line is the vapor pressure line in here in our case at an evaporating temperature of 4 degrees, and absorption is always going to be above the line and desorption is going to be below the line. And very important for heat storage here is we want to be able to perform close to this equilibrium line. And you also see that in this desorption, the gross temperature lift, the practical gross temperature lift is always going to be slightly greater than equilibrium. In the absorption, it's going to be less, and here we already can point to a loss in the gross temperature lift, or if we define it as the temperature effectiveness, would be the gross temperature lift in absorption divided by gross temperature lift in desorption. This is also further alluded to in the below mentioned publication. When we look at the vapor pressure equilibrium lines as stated based on the temperatures that we define, we see here that we already, because in the charging we have a higher condensation temperature than in the discharging, the evaporator temperature, we of course have gross temperature loss just due to the specific application. And also, more importantly, what we see here is that in the discharging, because of the low vapor pressure, we cannot discharge to the same final mass fraction as would be possible with higher evaporating temperature. So just pointing to the fact that it's very important to have a common basis on the temperatures that we work with. Now, if we go to have a look still in the theoretical evaluation on the volumetric energy density, very important to base this on the maximum volume of the storage material. This is done here in this diagram for sodium hydroxide, starting at 58%, and then depending on how much we can dilute it, we have a respective theoretical energy density. And I've drawn in two lines here, just pointing to the already due to the application and the different vapor pressures in charging and discharging. seeing that because we have lower vapor pressure in discharging, we could reach a lower energy density. In this case, the 162 kilowatt hours per cubic meter compared to the 190. One more time, this is in respect to the maximum volume, which in our case would be the charged, so separated sodium hydroxide from the evaporating water. Now, going into volumetric power, which is not really evaluation on the material level is not really possible here because it has a lot to do with components. But there is on the bulk scale, so on the gram scale evaluation, there are possibilities to see behavior. We have built a sort of a bulk level heat and mass exchanger device that I show here, a large evaporator condenser on the left side and an absorber desorber on the right side, connected with a flexible stainless steel tube. And what we do here is measure the mass uptake of a still film, in this case of sodium hydroxide in the absorber desorber. You can imagine it was quite challenging to actually get the scale only to measure the mass uptake and not also all sorts of effects due to the connections involved. But from this evaluation, I can show here one measurement where we have an idea of the power performance of this thin film of sodium hydroxide. The purple is the mass uptake, and then in orange and in gray and green is the power. And we see that once starting absorption here, so we started with concentrated sodium hydroxide, 58%. We have a tremendous peak of power peak at first. In our case here, we have about 36 watts at first, but very rapid decline of the power as the as masses or water vapor is absorbed and the concentration reduces. And after 30 minutes, we have only about 5 watts, but we have not reached the equilibrium state of our sodium hydroxide. And in other words, this points to the fact that for heat storage, where it is very important to be close to the equilibrium line to reach high energy density, we're going to have a heat and mass exchanger that is not power optimized, but needs to take in account the low power in the process of moving towards an equilibrium state of the concentration of the sorbent to the vapor pressure. Now, with this in mind, going to component design, in our liquid absorption heat storage, we find that this is a similar process as for example, a chiller or also a heat pump, absorption heat pump. Nevertheless, with including the storage in other words, the storage of concentrated sorbent and sorbate in charged state, and then discharged state storing of the diluted sorbent for recharging. We have a process where we need to be able to reach this maximum discharging in a single pass of the sorbent through the heat and mass exchanger. For this reason, we find for the liquid sorbents the tube bundle falling film heat and mass exchanger as used for chillers and for heat pumps is not ideal. So we've gone towards developing a spiral finned tube heat and mass exchanger, also reported in the below publication. And one of the main things that we reach here is we reach a much longer exposure time of the sorbent, which is needed to be able to move there towards that equilibrium line to be able to get those high energy densities. And we've done numerous tests with this here. For example, we have an exposure time of the sodium hydroxide of about 12 minutes in an ice counterflow, so we're able to cool down the sorbent right to the input fluid temperature and reach a continuous process and reach a maximum temperature gain, gross temperature lift, because there's always a fresh sodium hydroxide introduced to the top of the spiral fin. And we've tested this now in a lab scale setup with a single tube, as shown here. On one side, the absorber, desorber, a similar build, the evaporator, condenser, and here are now some of the performance or the performance we reached with our setup here, again shown in this gross temperature lift and mass fraction mapping. And the red here now, the equilibrium line at 20 degrees. At the moment, I show this equilibrium line because these tests were tested at these tests were done at a condensing and evaporating temperature of 20 degrees, which must state now, as we saw previously from the realistic temperatures, is of course not quite fitting. But nevertheless, as an example here, we can show that depending, for example, on the mass flow, so how much sodium hydroxide flows, grams per minute flows on the heat mass exchanger, we see that we're closer or not so close to the equilibrium line. Here on the left bottom is a discharged state, and it is seen that even though mass flow is increased, the 11 grams per minute compared to the 2.3 grams per minute, the power is not substantially increased, but we divert away from the equilibrium line. So we do see in these tests now that we have a limitation in the mass uptake, and so a lot of our work now focuses on working on increasing the mass uptake while still having long exposure times and being close to equilibrium, which is a must for high energy densities. So to conclude here, we've in the task been able to define the 4 basic processes and evaluate these, and show that on the process level there are benefits of some processes to the others. We've been able to define for building heating storage applications testing temperatures, which enable now to evaluate performance of material from evaluate performance from material level to component and system level, and also comparison of different materials and different systems is made possible in as far as these temperature profiles are abided to. And emphasis on the fact that absorption heat storage is a different similar process to sorption chilling and absorption heat pumps, but in a sense that we need to be close to equilibrium line because of the energy density, which of course in a chiller or absorption heat pump is not a major focus, or not a focus at all. For this reason, we need to be aware that often heat storage systems will require different types of heat and mass exchangers to the chiller and heat pump. Thank you for your attention, and if there's questions, I'd be glad to answer them.
Thank you, Benjamin. Very interesting insight presentation. Now we have a good last 20 minutes for some Q&A session. I would like to start with the more general questions, and Wim, I would like to ask you, we had a speaker who is interested in whether there's research going on to find compact storage materials that can work both in heating and cooling modes, meaning that if you have a certain period where you need cooling needs, you can switch over like to having a hot water period or whatever in the other part of the year. Please, Wim.
Thank you. That's a very good question, and I do not immediately know of research that is going on in this field, because it would be really a material that would be switchable. It has been discussed a few years ago to work on this possibility, but I'm not aware of a group now at the moment that is working on that. So another task for your new research group. Yeah, possibly.
Okay.
Yeah. It's very interesting. Yeah.
And then we have regarding other PCMs, phase change materials. I think there are a number of questions to Christoph. First, I would like to start with a general one. Somebody asked for a PCM material that could be recommendable for temperature range from 22 to 30 degrees.
Okay, so one of the materials I already showed in my presentation is calcium chloride hexahydrate, melting at 29 degrees C. And as this is a very favorable material regarding costs and energy density, in this temperature range, either using the calcium chloride hexahydrate itself at 29, or preparing mixtures with calcium chloride hexahydrate as one of the components would be an option in this temperature range.
Okay, perfect. Also regarding your presentation, there were some technical questions on your methodology. Somebody asked, which numerical method is generally accepted to design and analyze the behavior of phase change materials from India?
Yeah, well, this is a very broad question. I try to ask for more details. So for the PCM material on the material level, the simulations that the numerical calculations strongly depend on the type of material class. So we're using a model to calculate these phase diagrams, which can be used for salt hydrates, so for concentrated salt solutions. In other cases, for organic PCMs, you would need different numerical or different simulations because of the different nature of the materials, their different molecular structure. So for the material level, it depends on the material class, and for the system level, I think there's a huge variety of numerical methods. Yeah, and I wouldn't say that there's only one that is generally accepted.
Okay, still some research necessary. Then there was a specific question on your calorimetry. Somebody comment whether 2 Kelvin per minute might be a bit too fast.
Mm-hmm. Yeah, that's right. So for us, as we were, I didn't show that, as we were screening, really a large number of materials, more than 100. Yeah, the using 2 Kelvin per minute is a good compromise in order to check if the phase change from solid to liquid, so the melting transition, if this occurs in a single step. So for this verification measurement, the important question was is the melting occurs it in a single step, and therefore 2 Kelvin is a good compromise between accuracy and measuring time. Of course, if you want to analyze the material, its melting temperature more accurately, then you might need slower temperatures. Actually, in this IE8 annex, we also developed procedure for dynamic DSC measurements, and one important step in the procedure is to perform a heating rate tests in order to identify the proper heating rates. And usually, yeah, that's right, they are slower. I don't know, maybe around 0.5 Kelvin per minute.
Okay. Last question to your presentation. Somebody wanted to know more on this twist technology, the component that was developed in Munich.
Well,
I think that was Wim's presentation. Maybe a question to Wim.
Okay.
Yeah, it was in my presentation. I already also published the link to the website of this group, so that more information can be found on this group. It's from the Technical University of Munich.
Okay, thank you. Benjamin, a challenging question for you. An inexpensive TCM for about 150 degree. Market ready? Very specific questions here.
Yeah, this is very specific, and I'm sorry, I've got to pass on that one. We maybe Wim can give some more information. We work solely on liquid sorbents at EMPA, and these are low temperature for building applications, and we specifically look at these building applications, and 150 degrees is too high for us because we don't have these temperatures available for charging. So, but maybe Wim.
Yeah, that's a good question, because this temperature range, say between 120 and 250 degrees centigrade, is a difficult one. Most chemical reactions start at, say, 250, 300 degrees, and this leads to that only sorption materials, so zeolites or aluminum phosphates, would be suited for the intermediate temperatures as a thermochemical material. We at AE Intec work with zeolite 13X that will be charged by solar vacuum tubes at 180 degrees. So this could be one of the possibilities.
Okay. Well, I think that we have, from the names, actually, I have a feeling that we have a lot of participants from India. So I want to raise this question: what happens if you go into hot climates? Applying your test methodologies, does it work as well in hotter surroundings, or do you have to adapt your research on materials for compact storages, Wim?
The chances especially for sorption materials, is that they also can provide cooling. So this then there would be a double function of storing heat, but also storing the possibility to cool. And definitely, yes, also for PCM materials, if you look into applications for hotter climates, then the phase change material research will work more on cooling purposes, so temperatures to be stored below, say, 15 degrees centigrade, than for heating purposes.
Okay. Well, there was one question. I'm not sure who to address this to. It says, has there been research to use of metal organic framework (MOF) materials for thermal energy storage through moisture adsorption? I think that was probably
I
touched
can
in.
answer this
Yes.
one. Yeah, metal organic frameworks are say organic molecules with a metal atom that have the possibility to take up a lot of water, even more kilograms of water than kilogram of the pure material. They are being investigated at the moment mostly for heat pump purposes, and this is because of the high cost of the material. There has been up until now no real jump into the cost reduction for the production of these materials. So only in smaller quantities, these materials can find their way to a technical application, meaning that for instance, for thermal storage for larger quantities, like for daily or for seasonal storage, at the moment, these class of materials still are too costly.
Okay. There are now some questions coming up which are interesting as well, looking more at a strategic point of view. People are asking how to get an overview on, let's say, all the TCS project, like research projects worldwide, or maybe material-wise. Wim, how about overviews? Do you do a report on this in your task, or how can people access your knowledge and these big overview you have in your research group?
Yeah, we try to make overviews also through the link to our website, the task website. There are regular also some review articles. A recent one was, I think, 1.5 years ago on the different researches on Thermo Chemical area. But we do not pretend to know all the projects worldwide. The focus is on European groups, some Canadian, but to be honest, I'm not aware what is going on, for instance, in India or in China.
Okay, I think there seems to be some interesting contacts here, and people are asking for email contacts to continue the discussion. I'm sure, Wim, you had your email at the back of your presentation, and the presentations will be also available with the download of the whole audio of the webinar. So there's for sure a chance to get to know the speakers and get in contact with them. And, you know, maybe we should give again the indication that IEA-SHC.org has a website particularly on task 58. And under the icon publications, you find these regular publications of the task that Wim was mentioning.
Yes.
So there was another question looking into whether you can get information on the materials that are researched or developed. Can you maybe point to this Wikimedia page where materials are described, or is this not in this context?
Yeah, there's one wiki page being developed on phase change materials, and we are also working on a materials database, which is more developed for phase change materials. There are some, I think now some 10 to 15 materials in the database, and starting with sorption and thermochemical materials, chemical reactions. So the idea is that we have a common database in which only the say data, or mostly the data that have been extracted from materials according to the agreed upon measuring method, that these data will be published on this materials database.
Okay, thank you very much. Christoph, a question, a more general one to your side, asking you what you do against phase separation to overcome this phase separation of materials.
So basically, these kind of eutectics should not be subjected, or should not suffer from phase separation if the calculation was correct and if the correct concentration was measured. So, however, several other salts are not stable without, let's say, without either modifying the material or are providing some kind of anti-phase separation units on storage levels. So there are different types of possibilities. And regarding what the samples that I showed, there was one where phase separation occurred, and this is for us an indication that the correct composition, or that the composition was not correctly calculated. And then on material level, there's the possibility, for example, to use thickening agents. There's a lot of literature on that. That's a kind of gelling procedure. And the other way is to have a kind of mechanism of process on storage level to prevent this.
Okay, thank you. Another challenging question from my side, I just would address it to Wim. Somebody asked that it's regarding cooling 130 to 160 degree, and they said we presently use erythritol melting point 180 degree, but we would like to use a PCM with higher temperatures. Do you have any recommendations?
At the moment, no. I have to dive more into that. Perhaps Christoph knows more on this phase change material.
Yeah. So my suggestion would be, so erythritol, that's a sugar alcohol, and these are limited to temperatures in this range, and there's also always a problem in temperature stability, that the materials do not degrade then at higher temperatures, for example 200, 300 degrees C, mixtures of salts are interesting to be used as PCM. So not, as in my case, mixtures of salt and water, just mixtures of different salts without water. And this is used, for example, in concentrated solar power systems using molten salt systems, and you can use these molten salts also as PCM.
Okay, perfect. A last question regarding supercooling phenomena. It's modeling and overcoming this phenomena. How can you explain supercooling phenomena? Is somebody asking?
Yeah, well, supercooling is also a PCM phenomenon. So I showed you several heating and cooling curves, and supercooling means that the temperature upon cooling, where the crystallization, the solidification starts, this is somehow lower than the melting temperature. So you have some temperature offset, and that can be difficult in applications. First, in DSC measurements using small sample sizes, this is typically very large. We have a high degree of supercooling, and then going to application scale using, I don't know, 1 cubic meter of material, which is not laboratory but technical grade. Supercooling is usually reduced. And well, for modeling of supercooling, I think there it's best to check the literature. So there's no short answer to modeling of supercooling.
Okay. Well, I hope that all of our many question raisers are happy now, and we have at least tackled some of their questions. I would like to thank the 3 speakers for their really engaged presentations, and the audience for their very challenging questions. And I hand over to Jenny for the final words, and to wish you a nice evening or the rest of the day. Thank you very much.
Great. Thank you very much. First of all, to Wim, Christoph, and Benjamin for your excellent presentations, and to Barbel for moderating the session today. Your presentations were very well prepared, and I think we all got a very good overview of the technology. And thank you also to the audience for your conversation, for your questions, and the good conversation. I just wanted to make another quick announcements about the recording. It'll be available within the next one to 2 days after the webinar on ISES and the IEA Solar Heating and Cooling websites. For ISES members, you have access to all the ISES webinars and presentations in the member area. Another benefit of joining, so we welcome anyone to do that. A quick announcement about our next ISES webinar together with IEA Solar Heating and Cooling Solar Academy. It will be taking place in January. The date will be announced soon, so look out for our next announcements about it on an important topic of renovating historical buildings towards zero energy. This is from Task 59 of the Solar Heating and Cooling program. So very much looking forward to that next webinar with solar heating and cooling. Finally, we appreciate your participation and we welcome you to provide your feedback on this webinar. Please write to us at public.relations@ises.org with any comments or questions about this or other ISES events. And we also welcome you to complete the survey, which will be sent to you by email. It's important feedback to help us improve these events. And don't forget to follow us on social media. So thank you again, everyone, also for wrapping up on time, and look forward to seeing you at another webinar again soon. Thanks.